This begins part 2, starting halfway through gravitational potential energy, which depends upon a couple of choices. Everything's about choices. If you want to use gravitational potential energy, got to put Earth in system, because the object by itself can't do that thing where the two objects smash together and do stuff. In order to compare gravitational potential energies, or to put a number on gravitational potential energies, you have to choose your point of reference. How you're going to measure height. Where are you going to consider that the height, typically recorded as y equals 0? And you have to go back to your sketch. This is something you put, make sure you add this to your sketch so you can keep track. Once you have chosen a 0 point, and there's no right choice, there's no wrong choice, although some choices may make your life easier and some won't, you can put a number on gravitational potential energy with the relationship that's on your formula sheet. The amount of gravitational potential energy is equal to, this is not a good day for the pen to be acting up. Right, so let's try this. Carrying on. Oh no, you're kidding me, right? All right. Gravitational potential energy.
Wait, you didn't unpause?
Mass times gravity times y. All right, we got it. And let's talk about that quantity in slightly more detail on one more slide. Again, this is a relationship, not just a formula. This doesn't tell you what UG is. If you know UG, it can also tell you what the mass of the object in question is. Or it can tell you how high the object is. It's a relationship. And don't forget now, whenever you see UG, that's characteristic of our planet. If you're doing a real experiment where it's important to be as accurate as possible, use 9.8. But in any word problem or test problem you're submitting to me, just use 10. So think about what this means. The amount of chalk smashing potential some object has depends on its mass. It depends how high it is above the piece of chalk in question. That's the colloquial way we think of height 0. Where is your reference point? And it depends on what planet you're on. G is our shortcut for what planet we're on. Oh, right. Okay, good. Concerning positive and negative gravitational potential energy. Does UG have a direction?
Yeah.
Okay, this is treacherous. All these energy quantities are scalar. That is, they have no direction, just an amount. But what does it mean that UG at least can be positive or negative? Well, it's like the amount on your credit card. It can be positive or negative, but that doesn't indicate a direction. That means what you have or what you owe. Okay. What's the physical meaning of gravitational potential energy with a sign on it? Consider our example of a desk and a piece of chair on the piece of chalk on the floor. What if the piece of chalk we're interested in is not on the floor, but rather up here on the table? If all this was happening on planet Earth, consider an object like this. If this is the object in question, right here, it doesn't have any ability to smash this piece of chalk. But if we chose a different point of reference, it certainly would have the ability to smash the chalk down here. It's okay to use any point of reference in a problem. The reality still works, but your numbers may be confusing. So let's pick here, at this point, if the height is 0 at this point. Doing positive work on this block, for example, if we lifted it up here, it would now have the ability to smash that piece of chalk. Would be the mass times g times some positive number y. But if the block were down here on the floor, this has not just no ability to smash that piece of chalk on the table, it has less than no chalk smashing ability. Yes?
If it's off to the side, does it have any chalk smashing ability?
No.
That is a good question. That's a good question. This? Okay.
Could you represent it that you could like pick it up and like throw it?
You could, but let's be careful that we don't take chalk smashing ability too literally. The reference compared to another object at the same height, does it have more ability to do stuff like smash chalk? And the answer we give is no. At the same height, it's the same chalk smashing ability. It's the same gravitational potential energy, because this is due, the amount of gravitational potential energy in the system is due only to the mass of the object and the planet and the height. Okay? If you measure a height for this object on the floor, you're going to get some negative number for y. And as a result, you're going to calculate a negative value for gravitational potential energy. And don't panic. Let's do some positive work on this object down here. Hey, wait, I did positive object. I did positive work. Has gravitational potential energy increased?
Yes.
Yeah, it's still negative, closer to 0. If we continue to do positive work, hey, wait, now we're up to 0 potential energy again. The way you can think of this you can pretty much always, in a classroom situation, you can always get more energy out of a gravitational potential energy system. We can always find, another hole to push the object down. You could say that the gravitational potential energy works like a credit card in this way as well. If here's us about to throw a chair out the window of our classroom, and if this is height 0, in the initial state, when let's say Arvind was about to drop it out the window, the chair is not moving. It's at height 0. Let's specify our system. In the final state, my smartboard foo is weak today. In the final state, the chair is moving very fast indeed toward the ground. Where did all that, if we make a work energy bar chart for this, initial state, final state, if we're at heights, we're not moving, so in the initial state kinetic energy is 0. We are not elevated because we're at the chosen place where we decided we're going to call height 0. So UG is 0 as well. Clearly in the final state, there's kinetic energy. This chair is moving fast. Where did that energy come from? Did something do work? No. Okay. No work. No work. If Earth is in the system, work only happens when something outside the system adds energy or takes it away. And yeah, there you go. Work must be 0 because nothing from outside the system is doing any work. All Arvind is doing up here is letting go. That kinetic energy comes out of our gravitational potential energy credit card, like this. So as always, when reality checking a bar chart, you need to check 2 things. Do the numbers match up? That is before plus work equal after. In this case, it clearly does. Total 0 equals total 0. And does the chart match reality? For the system choices we've made and for the moments in time we've selected. And we're looking good here. All right, a little bit of elastic potential energy. This is the kind of chalk smashing potential you have in anything that is stretchy, that is elastic. The rubber band in a slingshot. The spring in a dart gun, perhaps. Oh boy, that's not my best dart ever, but you get the idea. A spring can be one that stretches or one that compresses. And in each case, we see the familiar pattern where a force in the same direction as an external force in the same direction as the displacement of the system object. Here's the displacement for the slingshot, and here's the external force. That's positive work, producing an increase in elastic potential energy. If you unstretch this, if you take this dart off the spring without letting its velocity increase or without letting it smash any chalk, we have a displacement of the system object in this way. And what direction does the hand push on the dart to ease it off of here? The opposite direction. So here's negative work. As in all of these things, before you go to calculate, think about what's physically going on. If elastic potential energy is increasing, something must be more stretched or compressed than it was before. No spring, no elastic potential energy. The wording of the question should make it clear. It's pretty unlikely that you should be putting in a spring or a rubber band if something is not mentioned to you. The quantities of elastic potential energy are not difficult, but there's some details. As it says on your formula sheet, elastic potential energy, the quantity is defined as little k, note the difference, x squared over 2. US is energy in joules, of course. Little k.
What is x?
X is the stretch. Or, let me make that absolutely clear, compression.
So that would be like what we did when we got it.
It is so like what you did. This is the difference between the relaxed state of the springy object and the state we're looking at. So this is something, this is not difficult, this is not rocket science, but this is a little detail we've got to be on top of. So if your springy object is like this when relaxed, if you stretch it, or if you compress it further, in both cases, you'd measure the stretch like this. Don't worry about the sign of the stretch, because this quantity is always a positive quantity. Mathematically, that makes sense because x squared is always going to be a positive number. Physically, it makes sense because whether you're squashing it or stretching it, now you can smash more chalk than you could before. Back to little k. Again, physically, what does this mean? Well, the amount of chalk I can smash with this springy object depends on how far the object is stretched from its relaxed position. No stretch, no energy. And it depends on what is the object I'm stretching. Is it a big, stiff automobile spring, a rubber band, a bungee cord, something in between? Well, that's what k is. Little k is the spring constant. Constant for every spring? No, constant for this spring. It's a characteristic of this object. Yep.
How do you find the spring constant if you don't have any measurements?
Good question. And let me just point out before I address that question, how do you find the spring constant? The units of the spring constant are newtons per meter. It's an index quantity, how far you have to stretch the object if you want it to exert a newton of force. And aside, we are talking about energies now. You are probably not going to have to concern yourself with any quantity that's not in an energy. For example, there's no place on your formula sheet where acceleration is involved. There's no acceleration in any of the energy quantities we have here as such. So if you're trying to find a velocity with an acceleration and a time, you might be misdirecting your effort. So let's go to Pete's excellent question. But how do you find little k? Because lots of energy questions seem to be giving us little k's or asking us about little k's. Let me tell you what you're not going to have to do anymore. You don't have to use the definition of the spring constant, stretching a springy object by a certain amount, measuring the force it exerts, plotting a best fit line, and then taking the slope of that line, which equals little k, the spring constant, in newtons per meter, the relationship between the external force exerted on the spring and the stretch, the slope of this line. You don't need this. In a word problem for the most part. This is forces. If you're asked about a spring constant, if you're asked to find a little k spring constant, you will find that quantity by finding what other quantity first? Yes. Wait, almost. But excellent anyway. Yes, if you knew to, you're going to find, in energy land, you're going to find a spring constant by finding this quantity. And what other quantity? And the stretch.
So you just always have to know the stretch and itself.
Here's the thing. You're going to have the formula sheet in front of you, and I'm going to make a later video orienting you to that formula sheet and summary sheet. But you remember relationships. You know that elastic potential energy is related to the spring constant and the stretch, like that. So this is a relationship between three quantities. We have a lot of three quantity relationships. If you know two, you can find the third. So if you are asked about a spring constant, you're going to want to find that in elastic potential energy. If you're asked about a velocity, are you going to use the definition of velocity, delta x over delta t? Probably not. Where will you find a velocity in energy land?
Use kinetic energy.
That's right. A velocity is part of, for example, big K kinetic energy. What do you need to know to find out a velocity? The amount of kinetic energy, the amount of mass of the moving object. But wait, Mr. D, part of your brain is saying, how am I supposed to determine the kinetic energy if I don't know the mass and velocity? Okay. Well, that's when the big picture view will help you. You look at your initial state and your final state, adjust your choices if necessary, check your system choices, and if you can set the problem up so that you know every other quantity, you do know the K. So you are practicing the skill of switching your mental focus back and forth between tiny details and the big picture. And this is a useful thing to practice. And we will get more into bar charts. We'll talk about the gritty and yet still somehow fascinating details in the next installment of our exciting video review podcast, coming soon.